Okay, all good? Well, let me give you a piece of advice to start. When you go to an Italian restaurant, do not drink more than 5 glasses of wine. Especially if you give a lecture the next day. I'll blame my Italian friends on the state of my brain this morning, and I'll do my best, but expect surprises. All right. So, um, yeah, I was thinking it's also a little sad that Fabian and I didn't coordinate more, because I see what he's doing is really so much related with what I'm doing, and it would have been nice if it had been done before, but that's the way it was to be, so sorry about this. So last time we did something very beautiful. We mapped the loop model onto a sort of free boson theory. I called it decorated. Let's keep calling it like this. And of course, you've understood that this free boson is almost the same as the one that Fabian is discussing. Only I tend, as a natural conformal field theorist, to think of it mostly in the Euclidean plane, which is really classical statistical field theory, while of course you could also study this theory by deciding to quantize, decide about some time direction and space direction, go from imaginary to real time, and really do quantum mechanics. So I am kind of implicitly thinking about the two ways at once, and I know it's a little bit confusing sometimes for people, but if you want to really understand the relationship with the way of quantizing the so also the other point is that my free boson is decorated. It's much more complicated than the free boson that you would get in the Kostelich-Thouless phase transition, for instance. And we are not finished really understanding what decorated means. But apart from these caveats, writing the action in Euclidean space like this, and with the convention that in the map from the arrows of the oriented loops to the boson, an arrow represents a domain wall of step pi. We obtained some results last time, which I want to remind you of. We obtained that, E naught was gamma over pi, where n, or square root of q, was equal to 2 cosine gamma. And this led us to, and there was also the other identity that G was 1 plus gamma over pi. Okay. So this is true for the dense phase. And as I illustrated last time, for the dense phase, if we take n equals 1, that's gamma is pi over 3, so G is 4/3. And what I didn't say last time was that we could also have studied the dilute phase. That's 1 minus gamma over pi. Sorry, that's for the dense phase. So it's 2/3, sorry. And for the dilute phase, the things would be essentially the same, only the coupling constant would be 1 plus gamma over pi instead of 1 minus gamma over pi. Otherwise, everything else that we said works just similarly. In particular, this identity does not depend at all on whether you are in the dilute or the dense phase. It only is a geometrical result, really. So this means that for n equals 1 dilute, we have now G equals 4/3 instead of 1/3. So let's look at these two examples. So once again, we have these loop models, dense and dilute. I told you already that there would be these two phases. And in the end, we give ourselves a given value of n. And from that value of n, we extract the number gamma. And from this, we get G and E0. And we calculate exponents using this set of numbers. So in particular, again, last time, we looked at the probability that 2 points are not separated by a loop. And we argued that, this was easy to obtain. All we had to do was choose for our 2 points as a particular observable what we called vertex operators. And we argued that all we needed to do was to have E1, E0 plus 1/2, and E2, E0 minus 1/2. If we did that, we would kill the weight. We would first of all, because of the E0, cancel the phases associated with going around the loops. And point number 2, with this choice 1/2, we would exactly kill all the loops that separate the 2 points. So as a result, we would only keep loops that surround these 2 points. And that's good because that's the observable we want. We want to know whether these 2 points belong to the same cluster or not. And again, last time I said that the dimension of the operators would be, so that was, in general, if we have e to the I phi and e to the 2 E0 minus I phi, which is the pair of operators we need to consider so that the sum of the two charges is 2 E0, the dimension turns out to be E times E minus 2 E0 over 2G, which is E minus E0 square minus E0 square over 2G. And last time I calculated the exponent in the dense phase. So in the dense phase, you would find with these numbers that D is equal to 5/48, while in the dilute phase, so what is the difference? Dilute, you would take G equals 4/3 instead of 2/3. In the dilute phase, we would get that D is 5/96. And that would tell you respectively that the fractal dimension in that case is 91/48. And in that other case, it is 187/96. Okay, not particularly thrilling. These are just numbers. I totally agree with that point. It's not very physical, but these are extremely important results. They give you the fractal dimension of the Ising clusters at criticality in 2 dimensions. That's for the dilute phase, where the clusters just start existing, so to speak. And this gives you the fractal dimension of the Ising clusters in the dense phase of the loop model, which is just the contours of spin domains in the high temperature phase. There's plenty of them. So the high temperature phase of the Ising model, which is trivial from the point of view of phase transitions, if you focus on the spins, for the clusters is highly non-trivial, and it has this fractal dimension. So This is something that physicists obtained many years ago, and then mathematicians managed to prove these results in some cases using strategies that I'm not going to be able to discuss. But this is the beginning of the field of what's called Schramm-Loewner evolution and the field medals of Wendelin Werner and Fyodor Smirnov in particular. Yes. Sorry, let me crank up my hearing aids. Yes, go for it.
Why can we deduce the dimension from looking at when two points are separated by a loop?
Yeah, this is something I explained last time a little bit. I'd rather not go into this very much, but the point is that if, so it is a general claim, and you may want to think of it, if the probability that 2 points belong to the object, whatever object you're considering, decays as 1 over r to the 2d, then the fractal dimension of the object is d fractal is 2 minus d. Okay. Yes. That's very easy to understand somehow. The probability that the 2 points belong to the object is the thing that we can naturally calculate in a field theory. Now, because there is 2 points, very crudely, the probability that 1 point belongs to the object goes like 1 over a length to the power little d. And that means that the fractal dimension of the thing you are looking at is 2 minus this. For instance, if you had the plane, every point would belong to the plane, so little d would be 0, and that would tell you that the fractal dimension of the plane itself is 2, which of course it is, but that generalizes. Yes?
How do we describe this fractal dimension in Ising theory using Bose theory, but Ising field theory different from Bose theory?
Yes, it is a fact that confuses people, but when you're telling me the Ising theory is different from a free boson theory, you are thinking of the theory describing the local spin interactions. This has nothing to do with the theory describing the clusters. Again, the information that 2 points belong to the same cluster is not encoded locally in the spins, and in fact, it cannot be formulated in terms of fermions. It is just something else entirely.
Yes, the 2-point function in terms of spins can be formulated in terms of.
So some observables, yeah, I'll talk about them in 1 second, some observables can be formulated in terms of both Ising and loops, but only some. So there's this structure like a set of Russian dolls, if you allow me, where you undo the first structure and you get another structure, and then you can restrict to other observables and you'll have yet another structure and so on and so forth. This is what happens. So this kind of observable cannot be formulated in terms of the fermions. That's just the way it is. It's why it's difficult, because if it were just a fermionic observable, we could study it very quickly. Okay? So let me carry on with 2. Yes. Between dilute and dense? Yeah, it is just, well, you would have to think just a tiny bit more, but it is that when we argue that some fields are marginal, there are several solutions to the equation determining the marginality. And you have to ask yourself what is the field that is the most marginal, or rather that is the least marginal. And the difference between the dense and the dilute phase initially is not clear. You just identify 2 possible solutions. That tells you there are 2 possible fixed points of the RG. And then you have to decide which one is which. So the only thing you can do is study the corresponding fixed points and conclude. And this is what we're going to do now. So another type of observable, which I could introduce using left and right moving bosons, but I don't want to do this. I want to remain somewhat really very Euclidean. So the other kind of observable, so we saw that this we call a vertex operator. And now we're going to introduce something we're going to call a vortex operator. So what is a vortex operator? And in the language of the XY model, it's very simple. It is an operator, meaning a field that has a vortex of arrows going around it. In the language of loop models, it's the following. We imagine that we draw a line between 2 points, and then we demand that when we go around the insertions, the field phi is not single-valued, it is multi-valued. In other words, we say that when we go around the insertion, phi should change into phi plus, and general normalization is that we demand that phi becomes phi plus 2 pi m. This is really exactly like a vortex in the XY model, where what would that mean? It would simply mean that the arrows around the point in the XY model would rotate by 2 pi. If I try to define my field as the angle field in the XY model, I must be able to account for this kind of thing which correspond precisely to discontinuities, defects, dislocations of the field by, in that case, 2 pi. So in general, we introduce this other kind of field. And what you don't want is that when you go around a pair, you don't want the field to be multi-valued. You want this multi-valuedness to somewhat be local. So this means that when you go around that guy, you should have phi goes to phi minus 2 pi m. Okay, so that's a general definition. We're going to look at these fields, and why are these fields important? Because, for instance, let us now ask the probability. So let's ask the probability that 2 points belong to the same loop. We are not saying that they're inside the same loop, we're saying that they're on the edge. They really belong to the loop. So this means I must have a geometry like this. Okay? What is the probability that this happens? Well, it's pretty tricky to find in general until you think about introducing these vortex operators. So let's imagine now that we break our rule that current is conserved, and we imagine introducing an object that creates a pair of lines, right? So let's ask ourselves, what is the partition function of the system if I introduce an object that creates a pair of lines, another one that absorbs the 2 lines, and in between, everywhere the current is conserved? If I demand this, I see that what I get are configurations like these, which are exactly the configurations I am after if I want the 2 points to belong to the same loop. Other than this, the other guys still they get their weight k to the b and to the l. These guys still give me the weight k to the b, but I have to be a little bit careful, because if I force the orientation like this, now if I go from one point to the next point, I may gather angular contributions that may not be 0. Here it looks like it's kind of 0 because the 2 points are horizontal, both on the horizontal, but I could perfectly well imagine that I have a configuration like this. So this loop went to the right quite a few times, right? And this one went to the left quite a few times, but nothing forces them in general that, yeah, in fact, it's quite obvious because when you go around, the total number of left minus right turns is equal to plus or minus 4. So if both loops go in the same direction, necessarily you get a non-trivial angular factor. So if I really want to count these loops without nasty phases, I must correct for these angular contributions, point number 1. And point number 2, now I must interpret the presence of the source and the endpoint as two vortex operators of this type. So in general, what I need to do to really calculate my two-point function is first put charges to kill all the angular dependency. And once again, when you think of it, it so happened that these charges are exactly E0, which is good because you don't want to change the weight of loops surrounding this whole thing. So once again, we get the non-neutral Coulomb gas. And on top of it, we need to think of vortex operators. So here we need a combination of vertex and vortex operators, which I could write in terms of left and right moving bosons, but I'm not going to. And now what we need finally to conclude is what is the dimension of these guys. And I'm just claiming that the dimension is very much like for vertex operators. We should calculate the dimension for vortex operators. It's a little bit technical. I'm not going to do it. Just want to give you the result, which is gm square over 2 minus E naught square over 2g, where m has been defined exactly here. Okay? So for the thing up there, we have m equals to 1. So d is g over 2 minus E naught, which is g minus 1 square over 2g. For only one line, interesting because it is the order operator in the Ising model, that's m equals a half. So that's g, d is g over 8 minus g minus 1 square over 2g. So for the Ising model at the dilute fixed point, that was g equals 4/3. We get d equals 4 over 24 minus g minus 1, that's 1 over 9 times 8 over 3. So that's 1 over 6 minus 1 over 24. That's 4 over 24, 3 over 24, which is 1 over 8. That's the dimension of the Ising spin in the Ising model. So we do recover, if we wish, some dimensions that would occur in the fermionic theory, but on top of it, we have the dimensions of these different vortex operators. Yes? Can you repeat that? Yes, in the operator. They should sit exactly at these points. So if you wish, if I were to use a notation for, so let's call these VE, and let's call in V twiddle M. What we must do really here is have V E naught V twiddle M equals 1. Okay, that's really what I meant. Which Sorry?
And only this is a good observable with respect to our action? Or?
Yes? Yeah, that's exactly what I mean, yes. If you wanted, you could write these in terms of left and right moving fields, if you know what I mean, but we don't really have to do that. So why do I focus on these guys? Why am I interested in these vortex operators? It's because I've told you very early on that the crossings would not be important in the dilute phase, but they would be important in the dense phase. So let's now look at crossings. So a crossing, in order to understand what really the dimension associated with creating a crossing would be in the loop model, I have to ask myself what is the dimension of the operator that creates not 2 lines but 4 lines. This is really a crossing. In contrast with something like this, which looks maybe like a crossing at large distance, but does not break the current conservation. So the dimension of this guy, I can calculate it just like up there, but now I have pi, 2 pi, 3 pi, 4 pi, so now m is equal to 2. So the dimension is now, what do I get? I get 2g minus g minus 1 square over 2g, okay, which is 2g minus g squared plus 1 minus 2g over 2g, which is therefore 2g minus g over 2. That's 3g over 2 minus 1 over 2g plus 1/2. Okay? So that's the dimension of the 4-leg operator. And now I want to ask myself, what is this dimension in the different phases? So remember, we had dense phase G was 1 minus gamma over pi, and dilute phase G was 1 plus gamma over pi, where n is square root of q, some if it's positive at least is 2 cosine gamma, and gamma belongs to 0 pi. Okay? So let's look at this dimension there. First of all, let's evaluate it for some numbers more. For instance, let's take n equals 2. N equals 2 is gamma equals 0. By the way, the dilute and the dense phase coincide. So that's G equals 1, where D becomes, it's not plus 1/2, it's plus 1, sorry. D becomes 3/2 minus 1/2, that's 1, plus 1, 2. So the 4 legs crossing are exactly marginal at this point. Okay. Now, how about the way they depend on G, the conformal dimension, the dimension? I can calculate dd over dg. That's 3/2 plus 1 over 2g squared. It's positive. Always positive. So the dimension increases when g increases. Where does g increase? Well, if I go in the dilute phase, gamma is between 0 and pi, g is always greater or equal to 1. So I see that right at n equals 2, 4-leg crossings may be marginal. In fact, they are marginal. And the model maps onto the Kosterlitz-Dowless phase. But away from n equals 2, in particular n equals 1, n equals 0, and so on, in all this phase, the 4-leg crossings are irrelevant. Again, because their dimension is smaller than 2. So I confirm a posteriori the claim I had made initially, that four-leg crossings did not matter in the dilute phase, because now I'm able to calculate the dimension of the associated fields operators, and I see that it is larger than 2, which means the RG eigenvalue is negative, which means perturbations decay at large distance, and so on and so forth. So that's a very nice verification of what we had been claiming. In the dilute phase, we don't care about crossings. It is something that's been checked numerically to some good accuracy. It's not so easy. For instance, you can take a self-avoiding walk and then decide to allow itself to cross itself at four-leg crossings, and you have to check that the exponents don't depend on the fugacity of these crossings, and that's true. Not so easy to check numerically, but it's true. Meanwhile, still because of this, since G equals 1 corresponds exactly to D equals 2, any G smaller than 1 will lead to a dimension that's smaller than 2. So four-leg crossings are irrelevant in the dilute phase, where G is greater or equal to 1, but in the dense phase, they are relevant. Because, again, G is smaller than 1 in the whole dense phase. This means that if we pack loops and then allow themselves to cross, we're going to flow to another universality class. So really, the phase diagram for a given n as a function of k, and let's call it, I don't know, lambda, the weight of the four-leg crossings. The phase diagram of the model as a function of these two couplings is something like this. So we have a critical point where the coupling lambda is irrelevant. And then if k, let's do it 1 over k. If k is larger than k critical, we do flow to the dense fixed point, which I represent like this. But the minute we allow crossings, we flow away from that fixed point. So this is how it looks. It is an extremely unstable phase diagram where, again, the instant you allow crossings, you flow away to another fixed point. And the question of the other fixed point and so on, all these questions are absolutely fantastic, but this is not what I want to discuss here. I want to focus on the models without crossing, right? So doing this kind of game, you can carry on, and you can calculate many critical exponents, fractal dimensions, and so on. So the first phase of the field, if you wish, was calculating all this more or less rigorously, and then people inventing more rigorous techniques to prove really that these are the correct exponents. In particular for self-avoiding walks, it was really a very big battle to prove the value of the critical exponents and so on. So that's the kind of question that I would say is the ground zero question in this field. What are the exponents? But I want to use the leftover time to tell you a bit about conformal field theory. So the problem of this kind of approach is that it stops here pretty much. This Coulomb gas, this decorated free boson, is a nice beast. You can calculate some things like the exponents a little bit uncomfortably, because sometimes you have various choices. You have to hope for the best. But that's where it stops. So if you try to calculate the 4-point functions, which are very interesting objects, or by the way, even the 3-point functions, So this kind of formalism does not answer questions like what is the probability that 3 points belong to the same cluster, let alone 4 points belong to the same cluster. It doesn't answer this. To answer this, you need to know the multi-point correlation functions. It doesn't say anything about symmetries. I myself was always very worried about what happened to the UN or ON symmetry. It seems to have completely disappeared from the picture. What is the role of the representations of ON and UN in this business? What is the structure of the Hilbert space, if I can define it? Where is the non-unitarity? Something several people have asked. All these questions need to be answered, and this strategy is not going to give us the answers. So one needs much more work. And a good way to think now is to think a bit about conformal field theory. So I had regrets when I had to decide what to talk about. I thought, yeah, I should talk about conformal field theory, but I'm so bored to talk about conformal field theory, and you can only give that many classes on the topic. So I decided not to, which maybe was a mistake. But anyway, now I'm stuck because I have 1 hour left, and I have to tell you everything about conformal field theory in 1 hour, which I won't, of course. So let me just tell you a few very, very simple things, right? So let's babble about conformal field theory. It is quite simple, in fact, once you have swallowed all the algebraic formalism that I introduced on the lattice earlier, because in a very precise sense, the conformal field theory formalism is the continuum limit of the lattice algebraic formalism. But it takes time to understand this, and we're going to start not by thinking about this at all, but by thinking really about a few very simple facts. So first of all, we're going to do something very important. We're going to introduce z is x plus iy, and z bar is x minus iy. Okay? This is the beginning of conformal field theory, where instead of using x and y coordinates, I'm introducing z and z bar. Okay? And now let's write a two-point function. So in general, we saw that, for instance, for vertex operators. We saw that, let's go back for a minute to the ordinary free boson. So we had something like this, was 1 over R12 to the beta square over 2 pi. Okay? Now let's rewrite this, first of all, in terms of z and z bar, which will allow us to introduce some nice notations. So now instead of 1 and 2, I'm going to write this as e to the I beta phi of z1 z bar 1, e to the minus I beta phi of z2 z bar 2. And now already I've done something that's slightly non-trivial, because once I give myself z, I have given myself implicitly x and y. X is the real part, z is the imaginary part. But I don't want to imply that my fields in some sense are analytic functions of z, right? They are not. So that's why I'm going to copy z and z bar in my notations everywhere. And this will read 1 over modulus of z1, 2 to the beta square over 2 pi. Okay, very good. Now in general, we're going to have to deal with observables whose two-point functions will have the form 1 over z1, 2, and we're going to call the exponents h and h bar. We're going to allow more generally, this is something we have to do, allow more generally for z and z bar dependencies that are a bit different. So of course, This case corresponds to h equals h bar is beta square over 8 pi. But more generally, we could have h and h bar different. So h plus h bar is still called the dimension of the field D. I may call it dO, so you're not confused with fractal dimensions or dimensions of space. And very often h minus h bar is called the spin. Why spin? Because if h is not equal to h bar, when z2 goes around z1, you're picking up a phase. So if z12 goes to e to the 2I pi z12, you get that this is transformed by a phase e to the minus 2I pi times 2 times h minus h bar. Right? Okay, yes. Actually, let's imagine just that we exchange the 2 points to start. Then we obtain this result. And now we would have to worry about what kind of fields we want to consider. The kind of fields I want to consider are only fields for which the 2-point function doesn't pick up a sign when I exchange the points. So usually this will lead us to having h minus h bar integer. It's not really necessary. We could, for instance, think about fermions, where h minus h bar would be 1/2. But for the time being, in this context of loop models, it is clear that the 2-point function should not really depend on whether I look at observables like this, with z1 to the left, z2 to the right, or like that, with z1 to the right and z2 to the left. It really should be invariant when I exchange these points. So we should expect that this is true. But don't worry about this if it's not clear. It's just a detail. The point is really, in general, we should allow for 2 different quantities to describe our correlation functions. And now let me make some very dumb observations. First of all, comment a bit about scale invariance. So there is already a little ambiguity here. When we say scale invariance, we really mean that the theories at the fixed point of the renormalization group, if you know what I mean. What this means in practice for our correlation functions is that they obey some extremely simple symmetry under scale transformations. Okay? This means that the 2-point functions obey something simple. What is that something simple? Well, let me write it in terms of R1 and R2 for a minute. If I look at the 2-point function of my observables, not at R1 and R2, but at BR1 and BR2. So say the origin was here. If I do a scale transformation, I send R1 to BR1, B being some number, say 3, and BR2. I mean something real. I mean, I take my Ising model, I take my clusters, I look at the probability that this point and that point belong to the same cluster, and then I look at the probability that this point and that point belong to the same cluster, not the same point, in the same Ising model. If my formula up there is correct, this correlation function is equal to 1 over B R12 to the 2D, which means it's equal to B to the minus 2D O of BR1, O of BR2. Okay. Now this is not scale invariance. Things depend on the scale, but it is what is more properly called scale covariance. For those of you who followed the calculation with the cutoff, you may observe that if I had kept the cutoff, I would have something different. I would have to ask myself whether I should renormalize the cutoff or not. It's a very important question, but it's not the question I want to address. I want to stick to this guy. So first of all, it's not invariance, it's covariance. Okay, fine. Now, what is conformal invariance? Conformal invariance is demanding a more general property than this. So conformal invariance inspired by the fact that our 2-point functions are invariant under translations and scale transformations. And rotations. Global ones. The conformal invariance is essentially a guess that these 2-point functions may be really covariant under general transformations, which are only equivalent locally to these, and these are conformal transformations. So we can postulate covariance under conformal transformations. And conformal transformations are transformations that are locally equivalent to combinations of these, and in 2 dimensions, they are simply the analytic transformations. So this is a sort of postulate which can be proven with a lot more structure than I'm going to introduce. So let's just think of it as a nice expectation for the time being. It turns out to be true, but it's something that not totally obvious to see. It's true for many theories, not true for all theories. Let's just postulate for now that it's true and see where it would take us. First of all, what would it mean, conformal covariance? Well, this would mean that a 2-point function of operators inserted at 2 points for a transformation W of Z, W bar of Z bar, should be related by some way like this one up there to the correlation function at the points Z1, Z bar 1, Z2, Z bar 2. Okay? And the way to relate these two can be understood simply, guessed simply based on what I wrote up there. So the way it works is that, sorry, let me move this to the left, to the right. So the general formula that would describe conformal covariance is this one. The equivalent of W of BR becomes now W, and more generally what we are saying is that the correlation function of O of ZZ bar and O of WW bar should be related by something that generalizes this. Now what is this up there? This is just involving the factor b to the minus 2d, which is really, if I move it to the left side, b to the 2d, which is b to the 4h plus h bar. sorry, b to the 2 times h plus h bar, it's really the Jacobian of the transformation. So what we are saying is essentially that this is true for global scale transformations. And even if we have only a local scale transformation where the local rescaling factor depends on where you are, we're still hoping that this is true. So this would be the formula that we should expect for scale conformal covariance. So it's a little bit tiny, but this is dw over dz to the h, which is really like the Jacobian of the transformation. So this is the initial hope of conformal field theory, is that another way to write it is that dw to the h d bar w bar to the h bar O of w bar behaves like a tensor. So the correlation functions of this guy are equal to the correlation functions of dz to the h dh bar dw over dz to the h, no, sorry, dz to the h dz bar to the h bar O of zz bar. This is the general hope of conformal transformations. If it's true, it's amazing, because if you take a conformal transformation that maps the plane onto itself, it tells you that there's a huge symmetry, point number one. Point number two, if you take a conformal transformation that maps the plane onto something else, it allows you to connect correlation functions from the plane to correlation functions on something else. And now that something else may be very interesting, it may be some non-trivial geometry, so implicitly there are a lot of new observations that are going to follow from this claim. Only it's not always true. So that's potentially a problem. So I suggest we take a break now, and after the break I'll carry on a little bit, explain what this has to do with the Virasoro algebra, and finally, hopefully, manage to connect, at least qualitatively, with the algebraic lattice approach of the beginning and give you some exciting new results. So thank you, and see you in 10 minutes. So when you have a scale invariant theory, so-called, this kind of identity really works for every field in the theory. On the other hand, it's a little naive to expect that this kind of identity might hold for absolutely all the observables. Why is it naive? Well, let's look at it a little bit more. So I rewrote things here, and now instead of the z and z bar, I'm going to allow myself very often to use the words, the letter CC, like complex conjugation, meaning I put bars everywhere. I don't imply that h bar is the complex conjugate of h, for instance. In fact, really, I want to think of z and z bar as independent variables. Really, in conformal field theory, you must think not of the complex plane, but the product of two complex planes. But that's a technicality. For us, it's mostly notational convenience. So I want now to argue that this cannot possibly hold for all the fields in the theory. Why is this true? Why is this the case? Well, let's assume it holds for some field. Okay? Let's assume we have a nice field O for which this holds. Then let's consider what happens to the derivative of O. Okay, let's consider, for instance, what happens to the chiral derivative of O. So let's consider the correlation function dw1 O of w1 w1 bar dw2 O of w2 w2 bar. Okay. can perfectly well ask myself about this kind of correlation function. Now, of course, something that's very nice about doing statistical field theory is that you don't have to worry about the orders of the fields you put inside your correlator. Very nice. And you do not have to worry about derivatives being inside and outside. Really, what we mean when we write something like this is just dw1, dw2 of O of w1, w bar 1, O of w2, w bar 2, which I could measure experimentally by looking at the differences between correlation functions at some point and at some neighboring point. Now, if this is true, I can calculate what I get when I look at this derivative. What do I get? Well, it's the dw1, dw2 of the right-hand side. And now, of course, d over dw is d over dz, dz over dw times d over dz. So when I calculate the action of dw1, dw2 on the right-hand side, I have several types of terms. I have the terms where I calculate the dz's of these guys, and because d over dw is dz over dw, d over dz, when I calculate the dz's of these guys, dz1, dz2, O of z1, z1 bar, O of z2, z2 bar, I spit out a dz1 over dw1 and a dz2 over dw2. So now I have dz1 over dw1 to the h plus 1, dz2 over dw2 to the h plus 1, and then I have what I call the cc part, which is not really the cc of that guy anymore, it's the cc of the previous one. So I'm just going to write it like this again. These are the same as a shortcut notation. I don't want to write dz1 bar over dw1 bar to the h bar, blah, blah, blah. The point is it's the same. I could really forget about these terms completely. Okay, so that's part of what I get. And that's good because now dz1, dz2 of this, hey, why don't I write it? dz1 of this, dz2 of that. And then I have a nice identity between the correlators of dwo and dzo involving a conformal, by the way, these are called conformal weights. I think I forgot to say it. H and H bar are conformal weights, they're called. So that's fine. It looks like the kind of term I would want to have. But the problem is when you calculate the derivative of the left-hand side, is that you have more terms. You also have terms when you take derivatives of these guys. So there are more terms. For instance, another term is obtained if you take dw1, dw2, not of the correlation function, but of the Jacobian. Aye, so if you do this, you get another term like, so now again I act with dw1, dw2 on the right-hand side. So I get also h square dz1 over dw1 to the h minus 1 times d2 z1 over dw1 square times the same for the second one, right? So that's dz2 over dw2 to the h minus 1 d2 z2 over dw2 square times O of w1 w bar 1 O of w2 w bar 2. So it doesn't work. This term is not at all of the kind I wrote earlier. This term I cannot put into this kind of representation because I have a second order derivative. And then I have the cross terms where I would take the derivative of this guy for, say, dw1, but dw2 would act on this guy. So it's horrible. If O behaves nicely, the first derivative of O doesn't behave so nicely. Its transformation property involves not only the nice tensorial structure, but also a structure with derivative. And imagine carrying on. Imagine calculating the transformation formula for the fifth derivative. It's completely horrible. So there is a mess in there, and a way to organize the mess, organize the way fields or observables, I use these two words really equivalently, transform. And this is where the algebra comes in. So the way to organize the way the observables transform is first introduce something that's called a stress energy tensor. I will explain physically what it means a little bit later. For now, let's just think of it as a particular field in the theory, T of Z. And in fact, there's a pair of such fields, T of Z, T bar of Z bar. And second, organize fields via their OPE, we mentioned that earlier, operator product expansion, with T. So whenever you have a field O, let's put it at the origin, what you're going to do is look at the operator product expansion, which may be hard to calculate, but it has some general structure that we control. And it's going to read sum over n of something I'll call lno over z to the n plus 2. What does this mean? It means that with each field O, like a vertex operator, I'm going to associate a family of other fields, which I represent by this lno action. I'm always in Euclidean space, so I don't really have the means yet to define properly the action of an algebra. So this is just what I'm going to do. I'm just going to define these fields as residues of the operator product expansion. So there is such a field, this stress energy tensor. It is like a current. In fact, it has dimension 2. And once you have it, you can do an operator product expansion with the other fields, with the fields in your theory. And this defines for each O a family of other fields. That's really the important thing to remember. Each O gives rise to a family of fields. And now it so happens that this operation of defining ln of O defined in fact an algebra. So the action ln O defines an algebra. And that's where this famous Virasoro algebra comes about. But really, this is just a way, if you wish, of organizing all the fields in different possible transformations under conformal mappings. So the algebra, it's a Lie algebra, and it has this form. Well, see this second term I'll comment about in a minute. But the first point is that if a field behaves nicely like this, so a field that behaves nicely in fact obeys that lno equals 0 for n positive. It is a sort of highest weight. So what you do when you have a field that behaves nicely instead of looking at all the derivatives, really what you want to do is look at the action of the stress tensor on these fields. This defines for you a family of fields. It's really like a algebra acting on your space of fields, and this algebra is determined by this commutation relation. So a field that behaves nicely obeys this, and then you build all your families the families of fields by acting with L minus P, where P is positive, and you create more fields starting from your first field. This is the way that we organize the different observables. So conformal field theory is this very formal way to think of things where we take all the observables in the theory and we ask ourselves, how do they transform under conformal maps? And the set of observables can be written as a sum of, well, what do you think? We have these fields, we act on them with these generators, these beasts I call Ln. So what we get is a sum of representations. And now we need two things because we have T of Z and T bar of Z bar. So like we have this algebra, we have another algebra with bars, and this I will represent as sum of representations of V times V bar. So I know it's really very fast, but remember the loop models, when we thought about the transfer matrix, we said, oh, the loop models will be decomposed as sums of representations of the Temple-Elib algebra. Okay? And I'm going to field theory, I'm telling you the set of observables can be obtained as a sum of representations of the product of the Virasoro algebra and the Virasoro bar algebra. This is not an accident. One of the claims I'm going to make is that in a very deep sense, the continuum limit of the Temple-Elib algebra is the product of the Virasoro algebra and the Virasoro bar algebra. And I'll explain a little bit more what I mean by this. But for now, we are not on the lattice, we are in the continuum limit. So the point is, it's a very important point. When you have a theory that's gapless, you have many different ways of organizing its Hilbert space because there are excitations of arbitrarily small energy. So it's not like when you have a gap, because when you have a gap, certainly the excitation with the smallest mass is a natural object to consider, and then you can ask yourself what happens if you have two excitations and so on and so forth. But when the theory is gapless, any combination of fundamental excitations gives you another possible way of describing the set of excitations. So for instance, if you have fermions interacting, you can describe the low energy modes using fermions, or you can bosonize and you can describe your low energy excitation using bosons. If you know a bit more, you could describe your low energy excitation using spinons, or you could describe your low energy excitation using the Virasoro algebra. So there's a bunch of different possibilities, and it's a very general statement that to solve a gapless theory, you need the right basis. And I know this sounds a bit bizarre putting it that way, but when you think of it, all the gapless theories we know how to handle, they're handled by changing the basis. Again, the simplest object of all being probably bosonization of the Turing model, right? And you have the Turing model, if you try to deal with fermions, it's utterly hopeless. But if you bosonize, then it becomes easy. But the basis of boson is very complicated in terms of the basis of fermions. And the point of conformal field theory, really abstractly, you can forget the stress tensor, you can forget everything, consists in finding the right basis for the space of observables. and that basis is expressed in terms of representations of this algebra. Okay, so that's some general statements. Now, where are we at? Well, where we at is that we have this algebra which looks very mysterious. In particular, it's an infinite dimensional Lie algebra, where the Temperley-Lieb algebra was not at all a Lie algebra. Well, that's kind of confusing. But very soon I'm going to go back to the transfer matrix and the lattice, and I'm going to try to give you a physical intuition of what these things are about. So for now, maybe bear with me. Just swallow the idea that this is a way to organize the fashion, the various fields in the theory transform under action of conformal transformations. And then we're having this number C that is now is time to discuss a little bit. So C is called the central charge. It is something I didn't mention yet, but I have to at some point. So C is called the central charge. And in the field theory language, it occurs as the residue of the two-point function of the stress energy tensor. So this is a very important result also. The stress tensor is an object of dimension 2. It's not renormalized with dimension, it's exactly 2. Like currents have exactly dimension 1. There are some non-renormalization theorems for this kind of objects because they correspond to some symmetry that is presumably, we think, true in the quantum theory. So that's one of the remarks. And the other remark is C comes as the amplitude of this two-point function of the stress tensor. It looks abstract, but I can tell you now that for loop models, the central charge is known, and it is 1 minus 6 g minus 1 square over g. So this is something we could calculate. I'm not going to do it, but it would follow from the same kind of considerations we have pushed forward so far. So in particular, when n is equal to 2, g equals to 1, that c equals 1. That's an ordinary free boson. The minute we move from n equals to 2, we start having different values of the central charge. And in particular, they may be negative, depending once again on the parameters you consider. So for n equals 1 dilute, you would find c equals a half, which most of you, I'm sure, know is related with the Ising model. And for the dense phase, you would find c equal 0. I don't want to get into this now. I want to be done quite quickly because I'm also getting tired. So this Virasoro algebra, okay, fine. So a lot of conformal field theory, therefore, is based on representation theory. This is, by the way physicists always solve problems. They formulate it as representation theory, and then they look into mathematics books, where usually there is something about representation theory that they can use, and back and forth. So solving conformal field theories, to a very large extent, would be based on wondering about representation theory of the Virasoro algebra. I don't want to do that. I want to finish by connecting to the very beginning of his lectures and the concept of transfer matrix and so on. So now I'm going to try to give a little bit of flesh to these very abstract concepts in order to illustrate what on earth the stress energy tensor could be in a lattice model and what this has to do with the Temperley-Lieb algebra. And finally, I'll be able, I hope, to tell you just a little bit about symmetries. So bear with me, and let's keep this somewhat in mind. But let's now use another aspect of conformal symmetry. So the first aspect of conformal symmetry, once again, is that fields transform differently, and that there's a way to organize these transformations by looking at the Virasoro algebra. Fine. Another use of the conformal symmetry, very powerful, consists in looking at systems in different geometries. So let's now use a special map which will take as W is L over 2 pi log of Z. Okay? So Z is the complex plane, and I imagine I have my initial theory in the complex plane, no finite size effect, everything is infinite. What I'm going to do is I'm going to map this plane onto something else obtained by the mapping W is L over 2 pi log Z. So if in the complex plane I have Z is rho e to the I theta, I see that I have W is L over 2 pi log rho plus I theta L I theta over 2 pi. So in the complex plane, when I go around, I come back to the same point. This means that in the W plane, what I'm having really is a cylinder. If theta goes to theta plus 2 pi, I must come back to where I started from. So this is a cylinder of circumference L. When I go around the distance L, I come back. And then this thing tells me that points near the origin map to W having a real part minus infinity, and points very far off map to points having a W real part very large and positive. So this corresponds to going towards the origin in the Z plane, and this corresponds going to infinity in the Z plane. Okay? And now I've mapped properties on the plane onto properties on the cylinder. Okay? So that's one mapping I can do. And one kind of exercise, which I'm not going to do, but we could, is consider other conformal transformations and look at how properties may depend on the conformal transformation. For instance, look at it numerically and compare with predictions from conformal field theory. So one exercise that people like doing, for instance, is look at a problem in the half plane, which would also lead to some discussion, but it's very similar, and then map the half plane to a wedge and wonder how the critical properties depend on the angle of the wedge. This is the kind of thing you can do if you want to play with conformal transformations and geometrical problems. And I want to do this, I want to keep focusing on this guy. Now, why is it so interesting, this geometry? This geometry is very interesting because it's the geometry we used in the transfer matrix description. Remember what we were doing in the transfer matrix? Although we never really looked at the periodic algebra, but nonetheless, what we did was we had a lattice model and we were describing various properties like the partition function and correlation functions by using this object we call transfer matrix that we express in terms of the Temperley algebra. So implicitly, I can, if I wish, discretize my theory, like my Potts model, and calculate things using my transfer matrix, the transfer matrix I had written earlier. And of course, we expect that the continuum limit of these results would give results of the conformal field theory. But I know what the result from the conformal field theory should be because I can calculate, for instance, the correlation functions of my two fields, my field O, assuming it behaves nicely, assuming it's the simplest kind of thing in a conformal field theory, I can calculate its two-point function after the conformal map. But now the conformal map maps the plane onto the cylinder, so I can, what I do in practice is I calculate the two-point function on the cylinder as, well, the usual formula, dz1 over dw1 to the h, times the correlation function in the plane. Oh, but the correlation function in the plane, I know what it is. It's 1 over z12 to the 2h, 1 over z bar 12 to the 2h bar. So I can calculate the correlation function on the cylinder. All I have to do is replace z by w on the right-hand side and calculate dz over dw. And if I do this, which I'm not going to do because it's a little late, I would get something very simple. I would get pi over L over sinh pi over L W1 minus W2 to the 2h, pi over L over sinh pi over L W1 minus W2 to the 2h bar. This is an expression that is quite pleasant. First of all, when the norm of W1 minus W2 becomes much smaller than L, you can approximate the sinh by the argument. So what you get is 1 over W12 to the 2h, 1 over the W12 bar, to the 2h bar. This means at very, very short distances, the correlation function on the cylinder and the plane is the same, which you should expect because at very short distances, the correlation function is only determined by local properties irrespective of the geometry. So that's reasonable. Point number 2, if W goes to W plus, if theta goes to theta plus 2 pi, W goes to W plus IL. If W goes to W plus IL, I hope I'm not having, yeah, this should be invariant. This should be invariant. Yeah, I seem to be picking up a sign. Yeah, maybe there's a factor 2 that's wrong somewhere. I would like things to be, well, no. Yes, if W goes to W plus IL, I get a factor e to the 2I pi h from this term and e to the minus 2I pi h bar from this other term. So I get e to the 2I pi times h minus h bar, and I said I would only consider h minus h bar integer. So this is equal to 1. So indeed, the two-point function on the cylinder is periodic, which it should be because that's the geometry of the cylinder. So we're kind of happy with that. And now I'm going to come to the point. The point is that I can expand this correlation function as W1 and W2 become distant on the cylinder. I can expand this, or maybe I can just look at the leading order term as W1 minus, so let's take, imagine we propagate that way, so let's take W2 minus W1 is much larger than 1. I can approximate this correlation function by, so I'm going to have some numbers I'm not really going to care about, and then I'm going to have e to the minus pi over L W2 minus W1 2 pi over LH, e to the minus 2 pi over L W bar 2 minus W bar 1 to the H bar. And that's, I assume my x-axis is like this on the cylinder and my y-axis is like this. So this is e to the minus 2 pi h over L times x2 minus x1 plus I y2 minus y1, e to the minus 2 pi h bar over L x2 minus x1 minus y y2 minus y1. Okay? So this is the leading contribution of this two-point function when the points become far apart. And why is this interesting? I can also write it e to the minus 2 pi over L h plus h bar x2 minus x1 e to the minus 2I pi over L h minus h bar y2 minus y1. And now imagine calculating this correlation function, not in conformal field theory, but from the lattice point of view. What do you get when you do this correlation function from the lattice point of view? Well, you calculate it using a transfer matrix. So when you calculate such a correlation function using a transfer matrix, here's your point 1, here's your point 2. What you have is that the correlation function is determined by, well, z, the partition function, for a very long system, let's call this length L, goes like the largest eigenvalue of the transfer matrix to the power L, and the correlation functions in general they should go like, well, you have to think a little bit, but it's typically the decay of a correlation function like this is of this type, where lambda is the largest eigenvalue, and little lambda is some other eigenvalue. This comes about because you can calculate all these correlation functions. Again, the transfer matrix, and then at some point you insert the field O, and then you propagate with the transfer matrix, and then you insert the other field O, and so on. So this is the general structure of the correlation function as, sorry, that's W1 minus W2. So what you deduce by comparing these two, and that's really where I wanted to get to, is that the transfer matrix of the StatMech lattice model in the scaling limit, that means when you look at energies much smaller than something of order 1, in the scaling limit, the transfer matrix of the lattice model should be something of the form, well, its eigenvalues should be essentially such that lambda over big lambda is equal to, so log of lambda over big lambda should be going like e to the minus 2 pi sorry, log of lambda over big lambda should be minus 2 pi over L times h plus h bar. Okay. So in fact, the spectrum of the transfer matrix in the scaling limit should be determined essentially by h and h bar. And something I think I forgot to say is that h and h bar can be nicely characterized by saying that the eigenvalue of the operator L0 on O is equal to h times O. So the thing I want to get to is that in the end, the transfer matrix is something like L0 plus L0 bar up to a small subtlety. So this provides a correlation between the transfer matrix on the lattice and the data from the conformal field theory. And in fact, you may worry about this. So like this is like the transfer matrix, and this would be like the momentum. So the momentum operator on the lattice is approximated by 2 pi over L times L naught minus L naught bar. So the important point here is that the transfer matrix and the momentum, they're both related with L0 and L0 bar. But now the transfer matrix was expressed in the language of the algebra. So what does it mean? Well, really what it means is that, in fact, there is really a correspondence. You can work out this correspondence to a very large extent. So the physical meaning of T and T bar is that, well, the Temple-Ellib operators, they're really like T plus T bar. In other words, T plus T bar is the local Hamiltonian density, something very simple, while what happens is that the commutator of EI and EI plus 1 is like T minus T bar. And what should happen if this picture is correct is that the continuum limit of the lattice algebra should be the Virasoro algebra, or rather the enveloping algebra of the Virasoro algebra. So that's a very powerful statement which would connect the lattice object and the Virasoro algebra. Okay. So therefore, to make a long story short, in order to solve the loop model, what you can do is study the representation theory of the lattice algebra, take its continuum limit with a lot of effort, and this gives you representation of the Virasoro algebra. So this tells you how the fields behave and so on and so forth, which is, of course, one way of proceedings to really solve the theory. Are you okay? I know it is fast, but hopefully you get the general picture, right? So we had Virasoro in the plane. We send it onto the cylinder and we do some mumbo jumbo, and we are saying that finally the Virasoro algebra becomes somewhat essentially the lattice algebra that we were having. So that's not so bad. The last thing I need to finish the calculation and finish the claim I made that I would tell you about the Hilbert space. The last thing I need to know is the multiplicities. So I had in the continuum, I said, oh, well, you know, the set of fields, which I could also dub the Hilbert space if I use the correspondence between 2D and 1D, is given by some sum of representations of Virasoro times Virasoro bar. And now on the lattice, I had a genuine space, the Hilbert space, or maybe some extension thereof if n is not integer, which I was thinking of as sums of representations of the Temple-Ellib algebra. Okay? And in both cases, what's really interesting is, so this is like the algebra of local energy and momentum densities, fine. What we're really interested is the symmetry. The symmetry is not there, the symmetry is in the multiplicities. So here and there, we're having multiplicities. And the question of what these multiplicities are is a question that's been really nagging people for quite some time because it's part of the solution of the theory and because it's the only way we can really understand what ON or AUN may mean if n is not an integer. So finally, in the last 5 minutes, I want to tell you about these multiplicities, which were found after quite a bit of work. And it's not even clear what they mean, although, well, okay. So let me write formally the Hilbert space of the CFT. So what do I need to write the Hilbert space of the CFT? Well, I'm going to write it in terms of representations of the Virasoro algebra. These representations are characterized by the conformal weight H. So I'm going to parameterize n of ON as 2 cosine pi over x. So gamma is pi over x. I'm going to look at the dilute model. It's the simplest case. So it so happens that with these conventions, C is 1 minus 6 over xx plus 1. And I'm going to use the parameterization, x plus 1r minus xs square minus 1 over 4xx plus 1. That's just a parameterization, although here, of course, this is nothing else but E0 square over 4g, quantity I've used earlier. So those of you who know about conformal field theory know that in ordinary nice conformal field theories, R and S, X is integer, and R and S take only a finite set of values. Well, finally, let me write this blasted Hilbert space. So H is, so we're having a sum over something I'll call chi d. So there are some notations, but don't mind them. These mean just some representations of the Virasoro algebra with labels R equals 1 and S integer. This is not the interesting part. Plus, we have a sum where R is a half integer and S belongs to 1 over RZ of, and that's really something a little bit complicated, we're having a multiplicity space times some other representation of the Virasoro algebra. So these are representations of Virasoro times Virasoro bar. Very interesting, but I don't want to get into them very much. This also, they're slightly different because there are some null states, but it's not much of a problem. What's really interesting are the multiplicities. And are the multiplicities, let's back up a great deal and ask ourselves, what do we expect from the multiplicities? Well, if we had an ON symmetry, we would think that the multiplicities come as irreducible representations of ON. For instance, the order parameter should come with a multiplicity n. It should come in a fundamental representation of ON. And in general, we expect every reducible representation of ON to correspond to a different conformal dimension. If you were to do epsilon expansion on the ON Landau-Ginzburg theory, you would find that every tensor corresponds to a different anomalous representation. And what we find is that it's not true at all. In this case, what is true, in fact, is that there are groupings of absolutely staggeringly large numbers of representations. So here are the content of the lambda RS in terms of representations of ON. So you see there is this label R that runs over the half integers. So for instance, the order parameter, where's the, thank you. The order parameter comes with the multiplicity n, indeed, that's fine. But very quickly, so the currents, ON has continuous symmetry, there are currents in the adjoint, so that's where the currents are. But as you go higher and higher in R and S, what you observe is that you're having a bunch of representations of ON that get mixed together. And so this is very important because the symmetry of these models is much more than you would expect. You would expect the symmetry to be Virasoro bar times ON. No, because it's Virasoro bar times something that glues together all these representations of ON. So for instance, the existence of these extra quantities is hinting that it's because they're there that the problem is solvable, although we don't really know how to make this direct connection, point number one. Point number 2, this connects with his recent developments on quantum mechanics and thermalization. If you were to try to thermalize this system, you should take into account the fact that it has more symmetry than ON. And in fact, these guys are representations of what's now called the commutant algebra. It was given the name Hubert Saleur some time ago because we invented them in 2007, I think. And third point, it also hints that if you want to define ON for n generic, not integer, you're going to have problems in general, and you may be forced to allow for groupings of ON representations into larger representations. So what the larger representation exactly mean is a little bit mysterious. There are generators connecting these representations. They're non-local. It's some sort of non-local symmetry, and this is something that's still being studied, but at least that's the answer to what I promised. This is the structure of the Hilbert space. There is a general formula for RNS, which is ugly, you don't want to see it. So that's the answer to point number 2, that is the structure of the Hilbert space. Now, the full solution of the theory would correspond to now taking any of these primary fields or fields in the representations of Virasoro and calculate their operator product expansion and calculate their correlation functions. This is something that's pretty much done now. I'm not going to discuss it at all. I just want to make one final remark for those of you who know about conformal field theory. This is a theory that's not rational in the sense that operator product expansions typically will involve an infinite number of fields. It is a little bit shocking, but that's true. So if you bring, for instance, two pieces of loop together and you ask yourself, how does this look at a large distance? In the OP, this will look like an infinite sum of observables. This is a non-rational theory and a non-quasi-rational theory. Sorry, I should say rather it's a non-quasi-rational theory. It's also a non-rational theory in the sense that even though the labels are rational, if you look at the conformal weights, they in fact, up to integer shifts, they're dense on the interval 0, 1. So you cannot organize the fields of the theory into a family of representations of some extended algebra like supersymmetry or something. In that sense, it is not a rational theory. Finally, these are not unitary theories because, remember, n, all this is a little bit formal, n is supposed to be a real number or a complex number, and when you have this property, and if you were to look at some more details about the theory, you would find, for instance, that the operator product expansions are not necessarily fully reducible. And in fact, the representations of the Virasoro algebra are also not fully reducible. They involve some sort of indecomposable structure, and they give rise to logarithmic conformal field theories, which is another kind of worms I'm certainly not going to get into. All right? So that's it. Thank you. Thank you. Yeah.